Hi, this is Mrs. LaBarbara. This is Regents Physics Chapter 2, Video 9. Today's lesson is Newton's third law. The objectives for today are note definition of Newton's third law, understand the connection between actions and reactions, understand action and reaction forces do not cancel out, be able to identify situations in which Newton's third law is needed to determine the reaction to some action. Newton's third law states, for every action, there is an equal and opposite reaction. This means forces always come in pairs, equal and opposite action-reaction force pairs. Here are some examples. When a balloon is released, air is pushed out the back of the balloon, and balloon is pushed forward. So balloon pushing the air and air pushes the balloon. Those are action-reaction forces. When you are rowing a boat, you're pushing the water back, but water is pushing you forward. Another example, when you're walking or running, the runner pushes back and down on the ground. The ground is pushing forward and up on the runner. Identifying and describing action-reaction force pairs is a simple matter of identifying the two interacting objects and making two statements describing who is pushing on whom and in what direction. So in this sentence, I want you to pay attention to two objects. So action-reaction are acting on two objects. So here are the three situations. First one, the action is the bat hits the ball. Reaction for that would be the ball hits the bat. So those are action-reaction forces, one acting on the ball, one acting on the bat, and those are the same equal forces in the opposite direction. The second situation, action, the ball hits the mitt. The reaction, mitts hit the ball. So those are one on the mitt, one on the ball. So those are action-reaction pairs. Last one, it's not so obvious. Action, the air is pushing the balloon out. That's why the balloon is not collapsing. But how come the air cannot come out? Because the balloon is pushing the air inside. So those are action-reaction forces. More examples. A firefighter directs a stream of water from hose to the east. In what direction is the force from water on the hose? So the water is going to the east. Where is that force coming from? The hose exerts an eastward force on the water. At the same time, water exerts a westward force on the hose. Action-reaction pair. A man getting out a rowboat jumps north onto the dock. What happens to the boat? Well, in order for the man to get on the dock, the boat has to push the man northward. The boat has to push the man to the north. At the same time, the man pushes the boat to the south. So as a result, the boat will move to the south. Another example, a 70-kilogram hockey player skating east on an ice rink is hit by a 0.1-kilogram hockey puck moving toward west. The puck exerts a 50-Newton force toward the west on the player. Determine the magnitude of the force the player exerts on the puck during this collision. So there are two forces. One is puck exerts on the player. The other one is the player exerts on the puck. Those are action-reaction forces. So the force the player exerts on the puck is the same, 50 newtons. Action-reaction forces do not cancel out. This is because they are acting on different objects. Take a look at the picture on the left. Here's a car parked on the parking lot. So the parking lot, the ground exerts a force upward to support a car, and the car exerts a force downward on the ground. Those forces cannot cancel out because they are not on the same object. One force on the ground, the other one is on the car. Take a look at another example, a car again parked on the ground. If we only analyze the forces acting on the car, then there are gravity force and a normal force, since they are both acting on a car, those forces can cancel out. That is, as a matter of fact, that is why the car is not in motion, because the net force on it is zero, because we can cancel out those forces. Another more examples. Take a look at this one. A fist is hitting the wall, right? And so one force is on the fist, one force is on the wall. These two forces are acting on two different objects. This is action-reaction force, cannot be cancelled out. Here is when you're hitting a ball on your head, there is a force on the ball, then there is a force on the head. They are equal and opposite, but they cannot cancel out because they are acting on different objects. Those are action-reaction forces. Now, when you analyze the force on a plane, you can have all different forces. You can have weight force, lift force, thrust force, and drag force. And those forces may cancel out because those forces are acting on the same object. So remember, action-reaction cannot cancel out because they are acting on different objects. But when we analyze just one object, all the forces on the same object, those forces can be added using vector addition. Now let's take a look at another example. This is just a box resting on the table. Let's figure out what are the forces acting on the box. So there's two forces, right? One is gravity, that's from the earth. The other one is the normal force, that's from the table. So FBG is the gravity from earth. And FBT is the table exerted force on the box. Now, these two forces are not action-reaction forces. And they do cancel out because they are acting on the same object, but they are not action-reaction forces. So what is the reaction force of the earth exerts on the box pulling it down? The reaction force would be the box is pulling the earth up. Now, what is the reaction force for the table, the normal force table exerts on the box? Well, the reaction force has to be the box exerts on the table pushing it down. That is a reaction force. Reaction force for both, for the first one, gravity, is the box exerts on the earth, pulling it up. For the normal force, is the box exerts on the table, pushing it down. Have the same magnitude and opposite direction. Another example, while driving down the road, a firefly strikes the windshield of a bus and makes a quite obvious mess in front of the face of the driver. This is a clear case of Newton's third law of motion. The firefly hits the bus and the bus hits the firefly. Which of the two forces is greater, the force on the firefly or the force on the bus? So, since this is action-reaction force, so they have to be the same. But how can you explain the firefly got killed but nothing happens to the bus? And that is actually due to Newton's second law. Newton's second law says acceleration is directly proportional to the force and inversely proportional to the mass. In both cases, forces are the same, but the mass of the bus is so much bigger than the mass of the firefly. So the firefly, the force has huge impact on the firefly, but it has no impact on the bus. Another example, true or false? As you sit in your seat in the physics classroom, the earth pulls down upon your body with a gravitational force. The reaction force is the chair pushing up on your body with an equal magnitude. So we know this is false. This is because both forces are acting on your body. So action reaction are acting on different bodies. Now, if false, correct answer. So what is the reaction force of earth pulling down upon your body? The reaction force is your body pulling on the earth, pulling it up on the earth. That's it for today. Thanks for watching. See you next time.